He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
Our calculations show that it's stable. Our calculations show that if we could create millions of these cupernicium atoms, it would want to form actually a metal.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it? If you split that in half, that would be nasty, wouldn't it?
Yeah, I think if you could manage to... Maybe we shouldn't talk about this. We'll give somebody an idea. So,
Yeah,
So this is...
Don't try this at home or in your garage.
Precisely.
You'll blow your neighborhood up.
Exactly.
I'm Brian Crump and welcome to Sci Fi, Sci Fact. This is a podcast where we take science fiction's strangest ideas, weirdest elements, and most unfeasible plot drivers and explore if they actually could happen. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy. If any theory exists. Here to tease out the plausible from the implausible in this particular piece of sci-fi plot narrative is Dr. Krista Steenbergen, lecturer of physics at Victoria University and associate investigator with the MacDiarmid Institute.
Congratulations, sir. You have created a new element.
Ironman is a great source of material for something like Sci-Fi, Sci Fact. Welcome to our latest episode, which returns to the imaginary world of Marvel Comics and Mr. Tony Stark. Maybe he's Dr. Tony Stark, I can't remember actually, but Iron Man, you might know him as. And we've already looked at Iron Man's suit and the plausibility of having a suit which allows you to fly around. And what else can it do? I think it's bulletproof and you can fire lasers from it or missiles or something like that. We're going to look at another aspect of Iron Man today and an element that he creates, Tony Stark, in possibly the second movie. I don't even know if it has a name apart from a nickname that it's given in the movie, Badassium, which sounds very Tony Stark to me. Anyway, now, we didn't talk to you about Iron Man. It was something else from Marvel Comics, wasn't it? Captain America and some element he created?
Vibranium.
Vibranium.
Yep.
What was vibranium again?
It's the element that is supposed to be, when you put it together, it forms a metal and it's supposed to be vibration resistant. And so, or it will absorb vibrations and create energy and then be able to retransmit the energy. So it was Captain America, but it also played a heavy part in the follow-on film based on Africa
Black
now.
Panther.
Black Panther.
Anyway, vibranium, is it in any way related to Badassium in terms of, well, it comes from the same family of imaginary comics.
Imaginary comics for sure. And actually, so I was reading a little bit of the background. It doesn't come out in the movies, but possibly in the comics. Somebody was saying, or somewhere online was saying, that the element that shows up in Iron Man 2, that we'll discuss in just a moment, the element that Tony Stark creates, was at some place called vibranium. But then later, evidently they dropped that. Yeah, it gets very confusing. Evidently they dropped that because then vibranium is mined from Africa in later movies, and so then it turns into Badassium or whatever
okay.
term.
They thought we have to create a new element because we've already got a plot story.
Exactly.
You know, we've got the storyboard for vibranium.
Yes.
And sorry, you can't use that now.
Can't use that now.
That was probably a boardroom decision.
Exactly. So
by
this
the
needs to be a new element for Tony Stark's suit. Otherwise, it sort of kills the plot of Iron Man 2. So
Can I just ask for a brief refresher, even though you didn't do Iron Man's suit, as to what makes it the suit that it is? I mean, I'm right. He could fly in it, couldn't he?
Yeah, he can
Was
fly in it.
Was it bulletproof?
I think it is also bulletproof, or at least mostly bulletproof.
Okay, and so you've got this thing which is kind of like an exoskeleton, but it's also a flying device. Now, what was powering that?
The arc reactor is what is the plot, at least the plot element in the movies. Again, I'm much more familiar with the movies than I am the comic series. So in the movies, it's this thing that's the arc reactor that Tony Stark creates, and the arc reactor definitely does play into the plot of the new element. So the new element is what he replaces. Evidently, in the original arc reactor thing is palladium.
Is palladium a real element?
It is a real element,
Okay.
actually. Palladium is a real element. I don't believe that you could use it to power anything. But having said that, it's a make-believe world, so they can use what they would like to use, and so they use palladium as something that the arc reactor, they don't get into it in the movies, but I think the implied story is that in any kind of nuclear reactor, you're going to split the elements to create energy.
Yes.
And so
it's a fission reaction.
Fission reaction, yeah.
Right.
And so without actually saying that, the idea would be that you split palladium to create energy that would then nuclear power
Right.
the
Flying suit.
suit, and also I guess all the lasers and
all the
blow-up
bells and
devices
whistles.
and precisely. So
Okay. But, I think one of the problems was that you split atoms, you generally create or release a lot of radioactivity, dangerous radioactivity. And isn't that something that actually happens in Iron Man, that dear old Tony Stark, because he's got this atomic reactor close to his chest, really rather close to his body, that he starts to get sick? Does that happen?
That's
Am I remembering rightly?
precisely the plot that leads to the creation of this new element, is that in splitting palladium, he's evidently creating nuclear waste of some sort, and he's going through a lot of these palladium reactor chips.
Does his hair start falling out?
Something along these lines. Actually, interestingly enough, it doesn't. They should have done that. They should have done that. No, he has blood toxicity, so it's getting into his blood, and then it creates some kind of toxicity, and this is obviously very bad, and so his health is declining, and he thinks he's going to die within the year, and he does a lot of silly things, and somewhere along the way, Nick Fury comes in.
That thing in your chest is based on unfinished technology.
No, it was finished. It was never been particularly effective until I miniaturized it and put it in my...
No. Howard said the arc reactor was a stepping stone to something greater. He was about to kick off an energy race that was going to dwarf the arms race. He was on to something big, something so big that it was going to make the nuclear reactor look like a AAA battery.
And says that your father says that you can create this new element, and he's given you the pieces for it, and locks him up and says, do it. And by some magnificent creation,
Is Nick Fury the bad guy?
Nick Fury, no, is the good guy. He does look like a bad guy for sure, but
He's one of those looks like a bad guy, turns out to have a heart of gold.
It's a heart of gold, exactly.
Palladium or something like that.
I think it should be palladium, so yes.
Right. So anyway, it turns out that Tony Stark's dad, Howard Stark, was also a brilliant scientist.
Yes.
And he had created this element, but then what?
So
died.
He hadn't created the element. What he did was he evidently, it's implied in the movie as well, had conceived of the possibility that this element could be created but lacked the technology.
Dead for almost 20 years. Still taking me to school.
The proposed element should serve as a viable replacement for palladium.
Thanks, Dad.
Unfortunately, it is impossible to synthesize.
And so he gave Tony the roadmap to create the new element in this design of
An cryptic crossword?
Cryptic crossword of some
like that?
sort. Exactly. I think, yes, this is it was the map of a not
some
a
sort of playground or something.
Yeah, it's a
wasn't
playground. That's exactly it. It was this map of a community that he left for Tony, and then Tony sees it after he's been told that his father left him the roadmap to do this, and he envisions it, and then he uses the computers to visualize it, and then he sees the element, and he chooses the element's nucleus, and then somehow, who knows? It's all in the story between the lines, right? So. But by seeing this, that his father gives him this, and then he can create this new element, he somehow sees through what his father leaves him, and then he manages to say, I think I can do this, and then hence creates the nuclear reactor in his particle accelerator in his garage.
Now, there's a mention in here of a tesseract. And a tesseract, I don't really understand, but I'm pretty sure Interstellar uses a tesseract as a plot device.
All of this is one little girl's bedroom every moment. It's infinitely complex. They have access to infinite time and space, but they're not bound by anything. They can't find a specific place in time. They can't communicate.
Because it's a tesseract inside a black hole that Cooper, the astronaut hero, uses to communicate with his daughter Murph, the scientist hero, that then works out the puzzle they need to solve to get them off planet Earth before Earth dies and create a new civilization in space. Gives them the energy that they need. And he communicates in space-time via a tesseract. So the tesseract, that suggests to me it's some kind of multi-dimensional device. Are you able to confirm that? You're looking slightly baffled there, Krista.
I am. It's been too long since I've watched Interstellar. It's terrible. You've actually given me the motivation I need to go back and rewatch the movie. I didn't remember the Tesseract showing up in that movie. It does show up as an intergalactic device in the Tesseract. Sorry, oh my gosh. In the Marvel comic series, it shows up as a device that allows you to transverse large pieces of space and space-time.
What's the connection between the new element and the Tesseract? Do you not know?
In Iron Man 2, I don't think that it is implied that the Tesseract is directly involved in this.
It's just
in the creation of the new element. Yeah, at least I don't remember it being in the movies. We go back to in the comics, it very much might show up. In later movies, the Tesseract is absolutely used as a device to create large amounts of power, and so you could possibly argue that you could use the Tesseract to create large amounts of power, which you would need in order to create the new element, right? So you would have to use a huge amount of power to accelerate things.
This is the thing, Krista. How could having something that is multi-dimensional, in other words, it's made of more dimensions that you and I can currently see or experience, somehow allow you to source more power? You'd be able to get power from other dimensions that we can't see. That
would be, I suppose, or it would, or it's possibly just the fact that this device has an enormous amount of power, and it requires that amount of power to connect to other universes. So it could go both ways, I think. So in other words, you need a huge amount of power. They've created an element within the Tesseract that generates a huge amount of power, and then that huge amount of power is what gives you the doorway. So that would be the way that would make more sense to me than the other way, which would be a device that draws power from the multiverse into the unit.
Oh, the multiverse.
Yeah, the right. the possibility of multi-universes.
We've been talking a lot about that on Sci Fi, Sci Fact recently.
Yep.
The multiverse. Anyway, that's an aside, but getting back to the Tesseract, and that's not the same as the multiverse. We're just talking about several more dimensions than we can see and feel and smell and whatever in our own world that might exist. And that might be a source of power. See, what I'm coming back to is that, as far as I understand, Tony Stark creates this Badassium, this new element, in his garage with a particle accelerator.
Yes.
Now,
exactly.
I thought that you had to have a particle accelerator about the size of a small country.
Yes.
To actually generate enough energy. Maybe.
How
does he do in his garage?
I don't think it's realistic in his garage unless you have to exist in the sci-fi world where maybe the arc reactor that he has generates more power than we would normally have here on Earth, and then maybe your particle accelerator can be slightly smaller. Instead of a small country, it could be maybe a small city. I don't know. Yeah.
Does it need to be so big, the real ones, like the Large Hadron, because it takes so long to speed the particles, get them up to 0.99% of the speed of light?
So so the research that I was actually involved with that plays into particle accelerators and creation of new elements, it turns out when you accelerate ions, which is what they do to create new elements, you don't actually need to have as large of particle accelerators as the ones that accelerate small particles. Okay, because what happens is you're not getting them up to necessarily 0.999 the speed of light. You have to get some of the atoms, not all of them, up to 0.9 the speed of light. So it turns out you can actually use smaller particle accelerators. They're still quite large, still probably not creatable in a garage, but they don't have to be the size of the small city. So they're not at the size that we're talking about when you are doing some of those small particle accelerator experiments.
Like they might be the size of what? Something like a rugby field.
Yeah,
as
I was
small as
actually
that?
looking this up. So I was amazed. There's pieces of the accelerator. There's a linear acceleration that exists that then feeds after you linearly accelerate the particle. It feeds it into the circular one, the cyclotron they call it. And the cyclotron is the one that's usually enormous and goes around in circles multiple times as they add energy on each cycle around, right? So the feed-in that accelerates evidently the atoms up to 0.2 the speed of light is only 120 meters, which I found phenomenal.
0.2 the speed of light.
Yeah, 0.2 the speed of light.
2/100ths of the speed of light. Or
Actually,
2/10.
1/5.
1/5.
1/5 the speed of
Well,
light.
that's a fair rate.
It is actually, and 120 meters is nothing, and so this is actually what they're able to do, evidently. And 0.2 the speed of light is pretty fast. So certainly faster than we can conceive. So of traveling. So 120 meters isn't so big. I think the radius of the accelerator was probably still on the order of maybe half a kilometer, or no, less than half a kilometer. Like maybe 200 meters
Okay.
for the radius. So still not in a house usually, unless your house is ginormous. So yeah.
I mean, he does have a big house, Tony Stark, doesn't he? He's a
Yep.
billionaire.
He is a billionaire
Or something
and
like that.
Yep.
But if he's able to get some power source from the Tesseract, maybe if you had enough power, you could have a small particle accelerator the size of a garage.
Could be.
Could be.
Conceivably, I think. I think the pieces of the experiment, again, what you think about with these particle accelerators are that you have the linear accelerator bit that gets it up to some speed, then you feed it into this thing that cycles it around. And what happens is as you cycle it around, you're just feeding energy into it on each cycle. So you're making it go faster and faster and faster. And so none of the experiments simply do one rotation around the loop. They always do multiple loops in order to get to the speed that they want. So if he has the Tesseract, maybe it can be smaller and maybe he just needs a few more cycles. The other thing I just had the thought of is that they direct these atoms in a circle according to the charge of the atom. It's missing an electron, say. And in order to keep it moving in a circle, you have to use magnets. So it's not just the fact that he would need a big garage, but you need large magnets to make it curve. And so I think
Maybe the magnets would be too big for the garage.
I think the magnets would probably be too big for the garage. So if you ever see schematics of these accelerators, there's these ginormous tubes on the outside, but the inside where the particles actually go is quite small. So you'll have something like a 2 or 3 meter outside tube, but the inside tube is maybe 10 centimeters.
What's in the outside tube?
Inside of that ginormous tube is a magnet.
Right.
So they have these series of magnets inside, large, extremely powerful magnets, and so that's how they end up directing the motion into a circular motion. And so it actually the reality, the sci-fi reality, the reality is quite sci-fi like. The creation of these experiments in order to direct these elements in these circles and speed them up. It's actually phenomenal science.
Have you been to the Large Hadron Collider? The
No,
CERN one?
I haven't.
What's the biggest one you've been to?
So I actually have not been to any of these. I'm a computational scientist. I do a lot of stuff on computers, and so but I did work directly with one of the gentlemen who was at the forefront of creating new elements and going in and doing these amazing experiments. And so he would tell us stories about going into some of these reactors around the world. Not the Large Hadron, because the Large Hadron is definitely one of the ones that is ginormous, city size, right? Small city size. And they do the small particle accelerations. So the ones that this gentleman was familiar with, they're quite a bit smaller. They generally accelerate ions, so atoms, the charged atoms. And there's one in Darmstadt, Germany, one in Dubna, Russia. Those are the two that were involved in the creation of the element that I've done some work on.
From what you're telling me, it's very plausible that you would create a new element in a particle accelerator.
Absolutely.
Is that the main way we create new elements?
So that is absolutely happening on a regular basis now. So many years ago, I should have looked this up, but I didn't. The last element in nature was discovered that we know of on Earth, and I should be careful about that because we don't know how many elements are being created in stellar reactions or in black holes or in some of these exotic, wonderful astrophysical objects that we know about. But here on Earth, the last element that we've observed in nature was element 103. I brought this in. I think it's called Lawrencium.
Lawrencium. It's a nice name, isn't it?
It is a nice name. And that would have been the last one that Earth would have created, or that has lasted, that we know of here on Earth. And then from element 104 on, these elements have only been created in laboratories. And so they're a group of elements that are called super heavy elements. And the experiments that are done to create them are very, in my opinion, science fiction. So it's real, but they very much feel like science fiction. And so what they do to create these things is they go into these ginormous particle accelerators, not quite Large Hadron Collider size, but still very large. And they take atoms, which are quite a bit larger than the tiny particles that the Large Hadron Collider collides, and they speed them up to very close, 0.9, approximately the speed of light, and then they bombard them into one another. So there'll be a source element that's just sitting still, and then there'll be an accelerated atom that gets accelerated up to very class, and then they slam that accelerated atom into the source atoms.
What do they normally use as the raw material?
So the one that I know of, which is the one that I did the work on, it was the creation of a super heavy element called cupernicium.
Cupernicium.
Yep, element 112.
Not named after Cooper from Interstellar, was it?
No, not named after, although that would have been spectacular. No, it was after Copernicus. Copernicus, yes. Also a worthy...
very, very
yes,
worthy.
Exactly. Yeah. And so the creation of cupernicium, the atom that they accelerate is radioactive calcium. So radioactive simply means that it's unstable. Calcium, obviously, in its normal form on Earth is not unstable, but...
An unstable isotope of calcium.
Unstable isotope of calcium, exactly. And so they accelerate that unstable isotope of calcium around in the particle accelerator at 0.9, approximately the speed of light, and then they bombard it into plutonium. The source sitting there is a plutonium source. And when the calcium hits the plutonium, not always, but when they're lucky, out the other side comes actually element 114, which is fluorivium. And then after a few seconds, it decays to element 112, which is the cupernicium.
Did they really have element 114?
Yes, they have observed quasi-stable forms of fluorivium as well. So, but at that point, when you get up to 114 and 116, you're actually, I think they have created up to 118. And
wouldn't this release, because this is nuclear fusion, isn't it?
Yeah, it is nuclear fusion.
You're fusing atoms under tremendous pressure.
Yep.
I guess that pressure is created by the speed at which they collide.
Yep.
And they fuse together for a moment, and there you are. You've got a brand new atom.
Yep.
112.
Is cupernicium.
For example. Yeah. Doesn't fusion release huge amounts of energy? That's what's happening in the sun, isn't it?
It is what's happening in the sun. And sometimes it does, but generally the enormous amount of energy that gets released when you do, say, a fusion reaction, it's a cascading reaction, right? So in a nuclear weapon, the individual atoms nuclear weapon is the other direction, it's fission, but the individual atom splitting, it does release an enormous amount of energy per atom, but it's the cascading. It's the fact that energy that gets released causes another atom to split, which causes another atom to split. So it's the aggregate of the number of atoms that split that causes the huge release of energy that, say, you see in the sun, and the sun goes the other direction, but it's the aggregate of a large number of atoms either fusing or fissioning.
So in this case, because there's only a few atoms involved?
Actually, the single calcium atom, right? And then it slams into...
A single atom of radioactive calcium.
Exactly.
Okay.
And so what you have is you have a controlled reaction that you have actually set up control so that it doesn't cause the cascade.
But it still will release for a certain amount of energy, wouldn't
it? The actual fusion in this case doesn't. So it requires the energy of getting the atom accelerated and then the bombardment. So you have energy that the calcium atom carries because of kinetics, because it's moving. And it requires that energy in order to get the fusion to happen. There will be some energy that you get originally when in this reaction, when it fuses to form fluorivium, that requires the acceleration. The decay process from fluorivium to cupernicium will release some energy. But again,
because that's fission now.
Yeah.
So you fused it, then it's splitting.
Right.
And splitting an atom also. So these two things, Is it only because we're dealing with such a small number of atoms that the
Yes.
energy that's coming out from
Yeah.
the actual nuclear reactions
Yes.
is not too major?
Very
Can
much
be
so.
contained within the
Can be contained
collider.
and is contained, yeah. So they will be very careful about
The
making
particle
sure
accelerator.
that it doesn't cascade. The other thing is that in order to get the large atom, the large energy from fission, let's go with that one because I know a lot more about I know more about fission than I know about fusion. The large energy from fission, say if you have plutonium, that's plutonium or uranium in an atomic bomb, right, or in a nuclear reactor, you usually are splitting into two relatively large cores. In other words, I don't know if it splits in half. I don't know enough about the reaction, but you might get plutonium and it'll split into two cores. So plutonium is weight 94, and each of the different cores that you're splitting into will be quite heavy each. Well, sort of heavy. When you have cupernicium, what actually ends up happening, you originally fuse the calcium with the plutonium, but then the decay reaction is actually only decaying by two. You have a very heavy nucleus and a light nucleus.
Right.
And it's not
Tiny
nearly...
bit sparks off.
Exactly. And when you only pull off a very small piece, much less energy is released.
Okay.
Much less energy is released in that kind of thing. The biggest amount of energy comes when you're pulling two relatively large things apart.
If we could split cupernicium into, what's half of 112? A 66. What's
50.
element number 66?
I think it's actually 56.
Oh,
and
yeah, you're right. It
would
is
be
56. 56.
Barium, which is also radioactive. So then if you could now create a cascade...
If you split that in half, that would be nasty, wouldn't it?
Yeah, I think if you could manage to... Maybe we shouldn't talk about this. We'll give somebody an idea. So,
Yeah,
yeah. So this is...
Don't try this at home or in your garage.
Precisely.
You'll blow your neighborhood up.
Exactly. So...
But the thing is, getting back to Tony Stark, and
Yep.
he's creating this new element, Badassium.
Yep.
But how long does cupernicium last for, hang around for, once
So-
you've created it?
So all of the super heavy elements have a very short shelf life. So the cupernicium in its most stable form only lasts a half a second.
Right.
So, and actually by radioactive standards, terrifyingly, that's quite a long time. So
Okay.
some,
So,
yeah.
Say Tony Stark creates this element. How is he going to keep it stable when it's so heavy?
That may be the most interesting part of the movie that I liked. I like the movies, by the way, quite a bit. But so if you watch that scene, he shines the Tesseract or some energy source, or maybe an ion beam. Let's make it an ion beam onto a little triangle that is probably we can think about that triangle maybe as plutonium if you go back to the experiments with cupernicium, right? And so maybe that ion beam that he's shining on is the calcium that we think about. So what he is doing when he does that is he would be creating not just one atom, which is what they do here, but he's creating a lot of the atoms. And so in that idea, he's making, or Sci Fi is making things more stable by aggregating. So you can think about when he's shining this onto this plutonium, instead of shining it on the plutonium and just bombarding it and then having something come out the other side that then decays, a single atom, in the case of the nuclear experiments that they do here. What he's doing is he's shining it onto there and sort of capturing all those calcium ions onto this, let's say, plutonium source that he's shining it onto. And now in that solid form, the theory is it becomes more stable. So by binding
Is
a
that
bunch...
plausible?
It actually is. So the work
But-
that I did,
Why, if that's the case, how come we haven't done it yet?
probably safety. The truth is I'm not sure. These experiments are extremely expensive and very difficult, and you don't always get, let's say in this case, cupernicium out the other side. But if they could make it more tunable so that you could always create cupernicium under certain conditions, the idea would be that if you can get a group of cupernicium atoms together. So I actually ran this calculation. So far, by the experiments, we've only created 8 cupernicium atoms. In the entire known universe on Earth, we've created 8 cupernicium atoms. And I don't know if you know anything about
That's not a lot of elements.
It's not a lot of atoms, exactly. So,
You wouldn't be able to see it. You wouldn't be able to see it with the most powerful microscope, would you?
Precisely. And then obviously they decay after a short period of time. But the idea is
Damn,
that
I got the thing focused and it's already disappeared. It's gone.
Precisely. So the idea is that if you could, in some imaginary universe, or possibly in the future, create millions upon maybe billions of these cupernicium atoms, the idea would be that you could maybe form a solid. Now, the second question is, would it form a solid? Would it bind? Would the atoms be happy together, or would they want to be in gas form? Because some things don't really like to be together. They like to be in gas form on their own, right? You can think about neon or argon. These things are very happy on their own, and they don't like to aggregate.
That lawrencium,
Yep.
the largest known element, 103, what's its natural form at room temperature? Do you know?
That we don't know, actually. My
Really?
guess would be, it's in the column with the gases. So the largest element ever created is in the column with the gases, and radon, xenon, krypton. And so you would imagine it would also take on a gas form.
Okay.
But the calculation I did on cupernicium, which again, because I use computers to run models, I can theoretically put a bunch of cupernicium atoms together, and our calculations show that it's stable. Our calculations show that if we could create millions of these cupernicium atoms, it would want to form actually a metal.
Okay, a couple of questions here. First,
All right.
if you're actually now dealing with a large number of atoms to
Yep.
create this triangle, this lump
Yep.
of cupernicium,
Yep.
which could be AKA Badassium,
Yep.
aren't you going to be releasing a lot of energy and fusing them that you're going to have to contain in some way?
That is incredibly difficult. So you don't fuse them in the case of creating. We go back to the movie, and if you go back to showing the ion beam on this, let's say, plutonium triangle that Tony Stark was doing this on. In that case, you're fusing each of the individual atoms, and then you might have that small decay process where it creates originally element 114 and then it decays to 112. And so there would be a release in that each of those individual decays from 112 down to 114. But the idea would be that the plutonium's already bound together in a solid form,
Yes.
right? And so you're not rebinding things. It's not actually a fusion process. It's changing each of the individual plutonium atoms into, say, a cupernicium atom, and then those cupernicium atoms happy to be bound together. So two cupernicium atoms sitting next to each other isn't the fusion process. Fusion actually involves the combination
Yes.
of the nuclei, right?
Yes.
And so two individual cupernicium atoms bound, or millions bound, in, like, let's say, a solid form, you don't have to fuse them together. You just need a binding between the two atoms.
And the binding element is plutonium?
The original element was plutonium. And then you would hit each of the individual plutonium. So the plutonium would be sitting there in a bound state, like plutonium bound together by some bond,
Yeah.
I guess, and millions of them. And then the idea would be the ion source would hit each of those individual plutonium atoms and then transform it into a cupernicium atom. And the cupernicium atoms would then each exist individually in a maybe similar matrix, I guess you'd say. But they would all be bound together as well. And so you'd have just basically a hunk of metal. And
What I think I'm understanding is that each individual fusion reaction is just that.
Yeah.
And that in itself doesn't release that much energy. And
Right.
then you've got a kind of a net here,
Yeah.
which, this is me trying to get it into my head.
No, it's great.
That then collects these atoms and allows them to bind and form a solid metallic
Perfect.
core.
Exactly
Okay?
correct. Brilliant.
So you
Yep.
get by the problem of, all right, we create a whole lot of this element without heating up the garage so much that it catches fire.
Or blowing something up.
Yeah.
Precisely.
Okay.
Yes.
Right, okay. That's the first problem.
Yeah.
Second problem, now you have this hunk of very, very heavy metal. Isn't it going to be giving off a lot of radiation?
Yes. That's, I think, the second piece. Well, actually, I have to be careful. Yeah. Sorry.
Because this leaves poor old Tony Stark. Not that I necessarily feel sorry for the guy because he's a bit up himself. But anyway, he's still got a radioactive thing in his chest powering his reactor. Because then he's got this new element.
Yeah.
It's still very radioactive. Yeah. It's still going to be a fission reaction in his chest.
Yes.
It's still going to give off radioactivity when there's fission reaction. How has he actually got through to pass go and get 200 this time? He's still going to jail, isn't he?
I think he's still going to jail, and arguably he's worse off, because in general you would expect the heavier elements, when they decay, they're going to decay to something nastier. as we just talked about, if you split 112 in half, you end up with barium. Barium is highly radioactive. I'm fairly certain it's one of the things that killed Maria...
Madame Curie.
Madame Curie, yeah. So, yeah. So
don't take that home.
No, exactly.
Don't put it in your garage.
So I think that he arguably has not gotten around the problem of this radioactive element. I mean, let's be clear. Palladium in its unbound form as a metal is generally considered relatively safe. It will form some nasty compounds. So if you join palladium with like chloride, it's disgusting. But palladium is actually used in some medical situations. It's generally considered, there's not a lot of bodily uptake. I forgot what it's called, bioreactivity or something like that. And so arguably I think that he started off much better than he will have ended up after he creates this new radioactive element.
Yeah.
But
see, that's the thing. This is where this one falls over in the end, isn't it?
I'm pretty sure.
Really, there's no way using nuclear fission to get your energy.
Yep.
The larger the element you're working on, the more radioactivity you're probably going to have to deal with. So creating a bigger element, however badass it might be, is not going to solve your problem. In the end, what he needs is a fusion reactor in his chest.
Yes.
Why didn't he just do that?
We should definitely let Marvel Comics know that in their future series that this is what they should do, that they can create a bigger, badder Iron Man suit, by doing this direction. So I agree. Yep. Very much so.
The power of water.
Yep, exactly. Or a byproduct of water, which is ideal, right? If you split two things and you manage to get water back out, that's beautiful. So, yep, I'm right with you. So, yep.
Thanks for listening to this episode of Sci Fi Sci Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci Fi Sci Fact on the RNZ podcast page. RNZ's podcasts are also available on Apple Podcasts, Spotify, and iHeartRadio, or pretty much wherever you find your podcasts. And make sure to follow us so you don't miss out on any new episodes.